the newborn. Sorry, I'm not skilled. Okay. As the formation of a ring and shocks in the Milky Way, in the interstellar matter. So, what happened during this formation of process? In fact, you have evidently a strong contraction. So you have an excess of angular momentum. So you form a thin layer of fastly rotating matter orbiting around the new star. And it's the credit of Victor Sapronov. It's not so well known, but in fact this man only 50 years ago described a series of phenomena leading to the formation from dust particles to rocks, to bigger rocks, and so on, finally to protoplanetary system and planets. So this the sequence of physical process to form a planet was not so well known before. And evidently, immediately you realize that in fact this kind of series of phenomena can happen around every star. So a priori, from 50 years, we can dream that you have a lot of planets in the Milky Way. So this kind of short movie to show the process is not a real thing. And you can see the series of phenomena leading to the agglomeration of particles and rocks connecting. It's not so easy. The physics of this phenomenon is not so well known. Still today we have some gap in the series of events, because when you have this rock of 1 meter, it's not so easy to stick all this. So the physics is not evident. So this is typically, you have a lot of work to understand this kind of physics. And in 95, so almost 20 years ago, the Hubble Space Telescope observed, to find what is observe the new stars in front of the Orion Nebula. The Orion Nebula is one of the big Okay, the first one. Okay, sorry. And choosing few young stars in front of the nebula, looking with the Hubble Space Telescope, they found some dark halo around every of these young stars. Why? Because the dust included in this rotating matter was enough to block the light coming from the nebula. And in fact, this is the place where you have the possibility to form new planets. So planetary systems do not require exceptional situations, because we have always an excess of angular momentum associated with the collapse of the matter. So we are going back to the same question. How many stars? Okay, dynamics can help to answer this question, but how many planets is not a real zoom, but it's not for the mind. If you zoom a small part of the galaxy, what you can see is something like this. So this is a picture of the center of our own galaxy. You see the peak of solar system. And evidently the question, how many planets are orbiting all these small dots? So the question is not to find new stars, where all the stars we want. The question is to find if we can find some planets. So this is out of the conference, but just to finish the study of where we are living. You know that also in '95, the Hubble Space Telescope did this very famous picture. The director of the Space Telescope Institute, Bob Williams, got some time where he can do what he wants. It's a very teeny part of the telescope time. and he decided to do one picture only, one photography. In fact, it's not only one, it's 10 days of series of pictures. And then after in the computer, you can go add all these pictures. And starting from the region of the sky where you do not see anything except 3 stars, 1, 2, 3 stars from our own galaxy. And after these 10 days of picture, of accumulating photons, in fact, he discovered 2,500 galaxies equivalent to the Milky Way in a very small, teeny part of the sky. So galaxies, like the Milky Way, are only test particles at the scale of the universe. So, okay, we can also dream, human, how many planetary systems could exist in this. Okay, no chance to detect. So, if we are really convinced that planetary systems are so frequent in the universe, it looks easy. We have huge telescopes. Astronomers today have huge telescopes, so we can imagine just to look the closest star around us and take a picture. And I believe this is still not possible, or almost not possible. Okay, I will show a few slides of real observatories and an observatory in Chile. Here you have the top of the Mont Paranal with 4 big telescopes, each one with a mirror of 8 meters of diameter. So my mirror is about the size of this room. So it's really big telescope in a very good climate here. So it seems easy. It's just matter to look the closest of a neighbor and to see if we can find planets. And happily, this story is not so easy. Because here you have the luminosity ratio between a star and a planet during the time. And you see that, for example, this curve here corresponds to the luminosity, the ratio of luminosity between a Jupiter-type planet, the big one, and the Sun. And you see, after a few billion years, like we are, in fact, the ratio is 10⁻⁹. So the intrinsic luminosity of Jupiter is 1 billion times smaller than the luminosity of the Sun. So you see that it's so difficult to detect such a planet directly by imagery, because you are always dominated by the light of the planet, of the star. So the problem is the problem mostly of the contrast of luminosity between the star and the planet. So nevertheless, some clever guy succeeded to do it for a few objects, and you see that about 10 years ago we start to have few detection, but in fact I would say they are not interested in planets. No, it's a joke. Because they are really massive planets. It's a huge planet, maybe 10 times the mass of Jupiter, and a very far distance of the star itself. So probably it's a different story. Skip this one. So, if we cannot do image of this planet, how we can detect the planet? In fact, it's very, very easy in principle. When you have the star and the planet here, in fact, you have an orbital motion of the planet around the gravity center of the system, and a rotation of the star itself around the gravity center. And we are not looking on this planet, we cannot see the planet, but we are looking at the star itself with a spectrograph to see small change of the wavelengths due to the Doppler effect. So the problem is simply to see the star and detect small variability of the velocity of the star induced by the gravitational influence of the planet. So evidently the principle is extremely simple. The difficulty is the amplitude of the effect, evidently because we are looking for object motion of about 1 meter per second or few meters per second. So you need an incredible stability of the spectrograph during several years, and you need to accumulate photons and so on. So this is a technical difficulty. So we start this kind of game 20 years ago, and at the observatory of Haute-Provence with an old 2-meter telescope, and we discovered a star with a periodic variability of something like 100 meters per second with a period of 4 days. And this was absolutely not expected. A planet with the mass of Jupiter with only a period of 4 days. So this corresponds to an extremely small distance between the planet and the star, maybe something like 10 times smaller, 20 times smaller than the distance between the Earth and the Sun. So the theory was not expecting to find this kind of object. So at the beginning, people do not believe that it was really a planet, because it is something similar. This is evidently a picture, a drawing. It's not a real picture. You see that if you have a star like the Sun and you have a Jupiter, extremely close, orbiting extremely close. What was the difficulty here with this discovery? The fact to form a planet with the mass of Jupiter, you need to accumulate a lot of matter, and you don't have enough silicates in the disk for the young stars. So you need to accumulate ice particles, and ice particles do not exist so close to the star. So how to understand the formation of such kind of object? And it's very strange to see that people don't read it well enough, the literature. Maybe you cannot read from the back of the... But you have a paper written already in 1980, so 15 years before the discovery of 51 Peg. In fact, a paper by two very important physicists in the States studied the gravitational influence of a body embedded in the disk of matter. Well, it could be a small galaxy in the disk of a big galaxy. It could be a young planet embedded in the disk of matter on the star. And he explicitly says that the interaction between Jupiter and the protoplanetary disk was studied, and the angular momentum transfer is shown to be so rapid that substantial changes in both the structure of the disk and the orbit of Jupiter must have taken place on a time scale of a few thousand years. So it's an extremely efficient phenomena to shrinking the orbit and bringing the young planet close to the star. So this is typically a cartoon of what happens when you have a young planet embedded in the disk. In fact, you open some kind of gap here, you induce excess of matter, and the reaction of this excess of matter lead to a shrinking of the orbit and the possibility to explain so short period, like we have observed. When a lot of questions still exist, how to stop the migration and so on, but it's not the problem of today. So, after this discovery in Haute-Provence, evidently the sky south of France is good, but you can find some place in the world with still better sky, and this is north of Chile. We have some desertic region. This is an observatory called La Silla, with several telescopes on the ridge, and so we start to observe, as our US colleague did the same in other place, in Arizona, and at the time a lot of new planets have been discovered. Today, I don't know exactly, I have not checked this morning the correct number, but we have much more than 1,000 planets detected by radiosity, by the techniques Doppler effect. You have something like 700 planets discovered by Kepler, and we still have 3,000 additional candidates. So the total number, I don't know what it is, but it's 7,000 of planets. And what we can see here, I've plotted the eccentricity of orbit as a function of the separation between the planet and the star. And you see that if you are looking only at the 4 big planets in the solar system, you have Jupiter, Saturn, Uranus, Neptune. All these 4 large objects are almost circular. So all the big planets of the solar system are with almost negligible eccentricity. And when we observe in the universe, it's a huge scatter of eccentricity, and evidently a lot of short periods. And this is absolutely not what we have in the solar system. So this is the typical eccentric orbit. You see the acceleration we have, it's a periastron here. So it's very easy to detect the eccentricity of orbits by the measurement of the velocity in the function of time. So here you have a long period drift plus an eccentric orbit. So, is it possible to go and detect much smaller planets by Doppler spectroscopy? So, we decide to move to larger telescope, to the 3.6 meter telescope at Chile. This is the dome of the 3 pins. Remember, when we are giving a size, 3.6 is the size of the diameter of the main mirror. So we build a new spectrograph with a sensitivity of about 10⁻⁹, so able to detect velocity change at the level of 0.3 meters per second. And we start to search for planets in the southern sky. And just, okay, I will not show all the objects we have discovered, but only just to see the difficulty. That here you have the velocity as a function of time. And evidently the red dots correspond to one single measurement. So night after night you measure, we measure and so on. And you see this kind of scatter. And what I do, you need evidently to have the help of a computer to analyze, because at the end you discover that you have 7 planets in this system. Evidently you cannot do it by hand to discover different influence, because if you have one planet orbiting one star, the velocity of the star will be something like this. If you have 2 planets, it will be something like this. 7 planets, more complicated. And this object, you see that you have a period as short as 1 day with about 1 Earth mass, here 5 days, 13 mass, and so on. So you see that the center of this system is extremely compact. So you have a lot of low mass planets extremely compact in the core. Evidently, we do not have system equivalent in the solar system. So this is a general rule we have, that the solar system is by no means a typical example of what we have in the universe. After several years of study, we have been able to do some kind of histogram of the mass of the object detected. And you see that, for example, if you look only the object with period shorter than 100 days, you see that the giant planets are extremely rare, but most of the objects we have discovered are about 10 times the mass of the Earth. Eventually, here we are biased because it's much more difficult to find planets here. So you have, in parallel to people doing some observations, you have also people doing the theory of the formation of planets. And you have, for example, 2 groups. One is mostly Daglin in the States and Shigeru Ida in Japan, and one of the team is in the Bern University in Switzerland. And they are putting all the physics of the agglomeration of to form planets. And they are able to try to study the formation of planets in disk, where you have here 1 astronomical unit, 10 times the 10 astronomical unit here, and here you have the mass, 1 Earth mass, then 100, 1000. So Jupiter will be at this level, and the Earth will be at this level. And so after, evidently you have a lot of free parameters, and we don't have absolutely the full knowledge of the physical process. And what you can see, this is the computer, and you see you have 2 things. One, the migration in that direction, and the increase of the mass as a function. And so after you can try to compare if the observation, the distribution of mass we have are something similar to what is predicted from the theory. Evidently, sometimes it's well, sometimes it's not so easy. After you have to form several planets at the same time and so on. So, going back to the problem of low mass planet, we would like to find planets in what is so-called habitable zone. So, in this kind of tree, here you have the mass of the star as a function of the distance between the planet and the star. And here is the sun, 1. You have the different planets of the solar system with the Earth here. And you can have some star matched with a smaller mass here. And you have detected several planets and so on. And the energy provided by the star is a dramatic function of the mass of the star. So the nuclear reaction in the core of the sun are much more efficient compared to the equivalent for this low mass star. It's about 100 of efficiency. So the net result that in fact you can be on an orbit much closer to this low mass star, and nevertheless you not to want to have some liquid water in the surface. This blue strip corresponds to the range where you can have liquid water on the surface of the planet. And today we have more objects, but already you can see as you have 2 objects detected a couple of years ago, showing that we start to have the capabilities and sensitivity to detect this kind of planets in the habitable zone, planet where we could dream that maybe the chemistry for the formation of a planetary system with life exists. So, what we can do in addition? Okay, we can measure the mass and the shape of the orbit, but we can do more. Despite we are not still not possible to see this planet. So the problem is called the planetary transit. You see that here, when you have a star with a planet orbiting, you can have time to time, if the period is short enough at least, the possibility to have this kind of planetary transit. So the global luminosity of the star have a drop. You cannot see evidently this, but you can only detect the small diminishing of the luminosity. And evidently after it's very easy, because the ratio of the contrast of the diminishing is directly a measure of the size of the planet. If you have the size, you have the mass by the Doppler spectroscopy, you have the density. So you can say it's a gaseous planet, a rocky planet, and things like that. So you can start to do some comparison of the physics, or internal physics of planet. And 15 years ago, something like this, we have discovered a planet with a period of only 3.5 days, and we have predicted the time of where you have a chance to have the eclipse of planetary transit. Evidently, it depends of the inclination of the orbital plane, and we do not know a priori where this inclination. And after is the problem of lottery. And at the exact time, couple of minutes, in fact, our colleagues observed this drop of luminosity, and immediately we have measured the size of the planet, we had the mass of the planet, and this corresponds to a density of 0.3 gram per cubic centimeter. And this is half of the density of Saturn. So this was the real proof of it is really gaseous giant planet. You know, still at the time, not everybody was convinced. So this is the same measurement, the same star. You see here from the ground the measurement, and the next season some US colleague repeats the measurement but using the Hubble Space Telescope. You see that what you can gain if you are going to space, the quality of measurement absolutely dramatic, and you cannot no more see the noise of the measurement, so you start to dream what you can do. I will skip this one. Oh no. Later, I will go back to the previous slide. Later, you have a US satellite called Spitzer in the States, measuring in the infrared. And this is the one measurement done by the Spitzer satellite. And this is the transit. When the planet go in phase in front of the star, here, and this when the planet is behind the star. And this drop here is related to the diminishing due to the emissivity of the atmosphere of the planet. And the emissivity is directly a measure of the temperature of the atmosphere of the planet. So we still not have the possibility to measure planet, but we can detect the shape of the orbit, the mass, the radius, the temperature in the atmosphere, and more. You see that it's not flat here, because you have some synchronization between the motion of the planet and the orbit, the intrinsic rotation of the planet. So you have something similar to the moon, the phenomena, and this could, in principle, explain this. But this not work so well. The reason why? Because you have some inertia of the temperature in the atmosphere of the planet. So you can do a lot of physics of this object. And for example, when the planet goes behind the star, in fact, the contrast of the small dip we have observed before is not the same in every wavelength. So if you repeat the measurement, in fact you can build the spectra in the infrared of the atmosphere of the planet and not of the star. So you can start to study the physics of the atmosphere of the planet. And this is absolutely a new domain of astronomy. So, okay, at the end, we have observed quite a lot of low mass objects by this technique. And here, for example, you have the radius versus the mass. This is a Jupiter-type planet. You have Jupiter, Saturn here. Here is a low mass planet, the Earth and Venus here, Uranus and Neptune here. And you can have some kind of curve with corresponding to the relation between radius and mass for different kind of planets. And if you zoom only for the low mass region here, you see that you have 2, 4, 6 times the mass of the Earth. Completely crazy, because you see that you have a huge scatter of density. So not all low mass planets are rocky planets. You have some planet with an extremely low density, so it could be maybe evaporated planets, evaporated low mass gaseous planet. So this is a new trend with a lot of study with new satellites to study this region. So next time, okay, we have discovered low mass planet, but they are always relatively close to the star. Do we have a chance to detect real planets? And here, the comparative size of the solar system planet. So, the size of Jupiter and the size of the 4 small rocky planets. The Earth is here. So, see the contrast between the size of the Earth and the size of the Sun. And in fact, when you mention we would like to measure the velocity of a planet, what is the meaning of this sentence? In fact, it's the velocity of all the atoms in front of you. But you have all the convective cells, and you have magnetic activity and so on. So the mean is not so well defined. So to detect the efficient, the gravitational wobble, the change of the velocity of the star due to the small planet like this, you see, is immediately extremely difficult because you have some kind of cheater. Nevertheless, astronomers are always very ambitious, and if you have the effect of a gaseous giant planet, Jupiter will be something like this, drop of when you have a transit, the Earth will be 100 times smaller. So the diminishing of the luminosity of the Sun, if you dream that the Earth goes in front of the Sun, is only 10 minus 4. So from the ground, no chance to detect it. And from the space, it's not so evident. But nevertheless, you have 2 satellites, Kourou, launched by the European Space Agency, and Kepler from NASA, have tried to detect this kind of object. And for example, Kourou detected a few years ago one object with a size as small as 1.7 times the radius of the Earth, but on short period. You see the difficulty, something like this. This is a real image. Here you have Venus going through the disk of the Sun. So you see, it's terribly difficult. And this is a cartoon from a NASA discovery. So it's not a real images. So what they have observed with a satellite a couple of years ago, here you have the luminosity of one object called Kepler 11. You see this kind of dramatic change of the luminosity at the level of 1%. This is only instrumental noise, because the satellite have some intrinsic problem and so on. So you can remove the low frequency you observe here, and when you have eliminated this low frequency, you have these measurements. So you see it's a lot of measurements. And here it's only 10 minus 3 here. And you see that you have a lot of bad value. Value is small. And what is the reason of this? It's not evident, because if you have one planet orbiting a star, you expect a periodic signal. And here, it's evident that it's not periodic. So after you can try to select the different reasons of this dip, and you see that it's due to 6 planets orbiting the same star. 6 planets orbiting the same star. This corresponds to an extremely thin disk of planetary system. And then after you can see that you have some. You have some small defect in the time of the different pixels, because the interaction between the different planets is large enough to be observed. And if you analyze this curve of the timing deviation, in fact you can derive dot by Doppler by this timing effect the mass of the planet. And Kepler discovered several hundred systems like this, a huge number of multi-planetary systems with several transits. So the ultimate goal of this kind of thing is to say, do we have a chance to detect life on such a system? So, to find objects with liquid water, we can ask why we would like to discover planet with liquid water in the surface. It's not an anthropocentric view. The reason is that the complex chemistry of life requires a very narrow domain of temperature. If the most basic characteristic of life is the fact that you transfer the information from one generation to another one. And how you can transfer this complex information. In fact, okay, we know from the existing life that it's a long chain of atoms called the DNA. And if you eat a little bit the DNA, you will destroy this long molecular chain. So the upper limit of the habitability is only a constraint coming from chemistry. If you want to transfer the information from one generation to another one, you should maintain the stability of the DNA. And on the opposite side, if the temperature is too small, in fact you will have almost no chemistry because it's too slow. So approximately, it's not exactly, but approximately this domain of temperature corresponds to where you have liquid water. In addition, water is very efficient. Do we have a chance? Okay, absolutely no chance at all. You have to keep at least this in your mind. No chance to go. If you detect a habitable planet, you have no chance to go and see directly. The distances are much too big to consider the possibility to go with a rocket or something like that. So the only way to detect life at distance is simply to analyze the chemical composition of atmosphere. And the idea starts from measurement done about 30 years ago. Here you have this infrared spectra of the Earth, of Venus and Mars. And you see a very specific characteristic here due to the ozone, oxygen, here, not present in the two other planets. And so, chemists have shown that the only efficient way to produce this kind of characteristic transition if you have biochemistry. Natural physical process cannot produce enough oxygen to explain this. So, seen at some distance, this is really a signature of life development in the atmosphere, on the surface of this planet here. So, and you see, you do not have anything on Venus, and you do not have anything similar to on Mars. So, and you have other chemical signature, possible signature. In fact, it is absolutely possible to detect life at some distance. So the question is, this is a sentence, the Nobel Prize Christian de Lure. So, do we have to consider life as a cosmic imperative? What is the meaning of this? So, if you have all the good conditions, temperature and so on, do we have a chance to see life emerging naturally as a natural process in the universe? So, I hope that maybe in 1 or 2 generations we will be able to answer this question. The situation of man in the universe. So, and I will finish with a few slides of the future. A telescope of 39 meters of diameter to be built in the coming years in the desert of Atacama. It's incredible. I don't know what is the length of this room, but it's not 13 meters. 39 meters. So it's a huge telescope. So to be located on this mountain here, Cerro Armazones, here you have Paraná, you see it's quite right. You have the James Webb Space Telescope, the next telescope after the Hubble Space Telescope. You have ALMA. This is an interferometer working in submillimetric wavelengths and millimetric wavelengths at 5,000 meters on the altiplano of north of Chile, with something like more than 50 antennas to study the cool gas in the universe, the formation of galaxies, formation of planetary systems, formation of stars. Fascinating instrument, and I have to thank you. I will be happy to answer your questions, not in Vietnamese, but with the help of some colleagues. Maybe we can discuss.
Thank you so much, Professor Mayor, for the very interesting talk today. And following the discussion session between students, lecturers, and researchers with Professor Mayor, please send us your questions. You can ask about his lecture and relevant to his research also. So for the student, you do not worry about language. We are honored to invite Professor Phan Bảo Ngọc to do the translation for you. So the student, you are welcome to send us the questions.
First question. Tiếng Việt đi nhé. Không biết tiếng Anh. Okay, good.
Hello everybody. I want to ask Professor Mayor some questions. The first, now today, scientific evidence that the entire universe is a holographic projection around the Earth. We are living in a holographic universe. Do you agree with me, yes or no? And the second question, a scientific question that related to religion. Do you agree with some ideas that there are life after life? Example, when we die, we go to another life, and then another life by life.
What is your first question? I understand the second question, but I don't understand.
The first question.
Nói tiếng Việt đi, tiếng Anh nhé. Mình dịch tiếng Anh.
Thời này các nhà khoa học gần như đã tìm được nhiều thực nghiệm chứng tỏ là cái thế giới chúng ta đang sống là thế giới là hình ảnh chứ không phải là những thứ cứng, có nghĩa là một thế giới mềm chứ không phải một thế giới cứng.
It's difficult to translate. Yeah? So it's scientific false evidence. He says that false evidence is our world is in fact we are living in is kind of imagination, right? Tưởng tượng phải không? Là tưởng tượng hay là sao?
Can you read this document? My English is not perfect.
Thế gì cứng là gì? Okay, the second question is why? If you die, then that's what happened later. Second question. Okay, so he can answer first, second question first, and then next first question later. Yeah.
It's a very interesting question of what will be the future of life. In fact, we have everybody knows that the history of life on the Earth, the problem of the complexity, growing complexity of organisms and so on. And man exists on the Earth for only 1 million years, something like this. So it's only a very teeny part of the history of the Earth. So what will be the future? And a lot of people believe that man exists today and will continue to exist. And it is certainly not the case. Because you have a lot of possible accidents. For example, you have the possibility of giant impact. This happened in the past, 65 million ago. Almost every 100 million you have a very dramatic impact, which may be erasing the life of a lot of organisms here. And we know that the control of the temperature of the Earth is due to the emission of carbon dioxide due to volcano. And the volcano, the motor of volcano is due to the radioactivity of rocks in the core of the Earth. So at the time, this radioactivity will decline, and people did some model of that, and about 1 billion years from now, we have no more volcanism, and probably we will have a diminishing of the temperature on the Earth, dramatic diminishing of the Earth, and many other possibilities. So, and probably the most important one, but I'm not expert in the domain, is the problem of the stability of biology. You know that organisms do not exist forever on the Earth. So we have to be facing the problem that not only men are limited in time, but humanity will be limited in time. It's a fascinating story about it. We don't know exactly what it will be the end, but certainly we have an ultimate limit in 5 billion years from now. We do not have any hydrogen in the core of the sun, so the temperature of the sun will increase dramatically. So first increase dramatically, burn the Earth, and then after decrease to very low luminosity. So it's a sad story of the long term.
Yes. I agree with you that there are a lot of planets, billion of planets, but I think there is one only. Do you know Professor Tim Shelton, Virginia University? Tim Shelton, he teach about the universe. It's so lucky for a planet to be a world.
Yes, I believe this kind of argument is not of very big weight for me, because on one side you have this huge number of possible planets where life could be possible, but on the other side you have what is the probability of life development, and nobody can answer this question. And it's typically a problem of badly defined mathematics. Infinite times zero, what is the answer? In fact, we do not know. We have no way to estimate the number of planets with living organisms. We don't have this. Okay, you have a lot of people speculating on the number of living organisms in the universe, but we do not have any. After you can have your own feeling, but it's no more science. You can have your feeling.
The last question. Do you know the left face is different from the right face? Left face different from the right face.
Yeah.
So you show a lot of number, the same number from the Earth to another planet, the same number, but there is one thing that we cannot say, we cannot define it, make the Earth different from the other. Can you talk about it? What do you think about it?
Nói thêm cái là
Vâng, là giáo sư đang chứng minh là nếu có nhiều thông số giống nhau, mà trái đất chúng ta có nhiều thông số giống ở hành tinh khác, thì khi trái đất có sự sống thì hành tinh đó cũng có sự sống. Ý của giáo sư là vậy, nhưng mà ý em nói là còn có những thứ mà con người ta không thể nhận biết được. Ví dụ như là cái mặt trái với mặt phải nó cũng không giống nhau.
Yeah, I understand. So the question is, for example, planets, other planet have same temperature as we are looking at the spectrum light, then the spectrum is something we cannot recognize.
Yes, it's very difficult to answer because it's true that, okay, the chemistry of life is mostly based on carbon atom, because the possibility of to have complex chemistry based on carbon is much higher than on other complete other different atoms. And in any case, we have all the possible atoms existing everywhere. It's not the problem. Always we have carbon everywhere and so on. So the problem, is it possible to dream to have a completely different form of life built on the carbon? Because except carbon, you have no chance of complexity. But it's true that life on Earth is using only 20 amino acids. We have 500 amino acids. Why they have chosen this 20 and not others? But for me, it's not really a problem. If life could choose different kind of amino acids and build a complex chemistry, why not? But nevertheless, the range of temperature is driven by chemistry. If you eat any kind of polymer above 100 something degree, you will destroy polymer. So this will be true with other different kind of amino acid. So we do not have any a priori on the detailed chemistry of other life in the universe. So, but nevertheless, we have some rules. We cannot say anything. We have to still stick with the law of physics and chemistry. Many years ago, 40 years ago, people was doing brainstorming to find a crazy idea of different kind of life. But very difficult to transfer the information of how to work, exchange energy, transfer this information to your descendant, it's not easy to do. But the only way you know, it's this long change of atom. Okay, the detail of the change could be extremely different from one species to another. But nevertheless, we don't know. Okay, you can have a hard drive of a computer, but nature do not produce this kind of device naturally in the universe. So I believe we have to respect a minimum of imposed rules from science, chemistry, physics.
Các bạn có cần phải dịch mấy câu hỏi và tôi hỏi nhau. Câu hỏi thứ nhất là sau khi chết là gì đó? Chết là thể theo là gì thì giáo sư trả lời theo một câu hỏi khoa học, tức là đến một lúc nào đấy thì cái mặt trời của chúng ta là mất cái là hết cái hạt phần hạt nhân bên trong, thì lúc đó nó phình ra thì như vậy thì nó sẽ cái vỏ của nó sẽ chạm đến trái đất, và như vậy thì trái đất sẽ bị hủy diệt và bốc hơi. Thì như vậy thì đằng nào thì khoảng 5 tỷ năm nữa thì chúng ta chết cả. Thì điều đó đã xảy ra, hoặc là có thể là xảy ra sớm hơn, tức là có những cái impact, tức là những cái asteroid đó, tức là những cái thiên thạch nó va chạm vào thì nó phá hủy. Thì đấy là một trong những cái giả thuyết cũng là giống như là sự gọi là tuyệt chủng của khủng long, thì có thể nó xảy ra sớm hơn là 5 tỷ năm nữa. Còn có thể là cái câu hỏi thứ hai, cái hỏi sau đó là tức là có thể là có những cái kiểu sự sống khác, thì giáo sư nói là có thể, tức là ở đây hiện tại thì chúng ta chỉ coi là cái đất và những cái điều kiện sống bình thường là giống như là một cái chuẩn để mà chúng ta tìm, chứ còn có thể là có những cái điều kiện khác của chúng ta không phải là vẫn chưa biết. Đấy, thì câu trả lời như vậy. Ok, thì bây giờ có ai có câu hỏi khác tiếp tục thì chúng tôi trả micro.
nói được câu đầu tiếng Anh. Cảm ơn giáo sư. Em muốn hỏi là em muốn nói là em nghĩ là chúng ta sẽ không có được câu trả lời nếu mà không có câu hỏi đúng. Thì em muốn hỏi là một câu hỏi có vẻ rất là cũ nhưng mà cũng rất là lạ, đó là tại sao chúng ta lại đi tìm một hành tinh khác giống như là trái đất? Có phải là vì chúng ta muốn tìm một lối thoát, tìm một ngôi nhà mới, tìm một nguồn năng lượng mới, hay là tìm một cái khoảng đất nào đó rộng hơn? Thì cái câu hỏi đó có vẻ như là rất là cổ, nhưng mà em ở đây muốn hỏi lại cái này là có nghĩa là đã bao nhiêu thời gian trải qua chúng ta vẫn chưa tìm được một hành tinh hay một trái đất thứ hai nào như thế. Thì có phải đó là lý do của chúng ta như thế? Có phải lý do chúng ta vẫn chưa là chính đáng? Em nghĩ chúng ta sẽ tìm được một trái đất khác nếu chúng ta có một lý do khác. Thì lý do đó có vẻ như là không ai nghĩ tới. Nếu chúng ta tìm một cái trái đất thứ hai chỉ để cho vui thì chúng ta có thể tìm được hay không? Thì em nghĩ là chúng ta đang tìm một hành tinh mới ở những không gian xa xôi. Thì chúng ta đang tìm ở cái không gian đó là không gian về thời gian, có nghĩa là không gian 4 chiều. Vậy chúng ta có thể có vẻ như là chúng ta không có thể cảm nhận được một chiều không gian thứ 5 hay trên đó. Vậy có phải đó là chúng ta đã đi sai hướng? Mỗi chúng ta là một vũ trụ, và nếu chúng ta tìm hiểu chính chúng ta tìm hiểu chính vũ trụ chúng ta, khi chúng ta mở rộng được nó thì chúng ta sẽ tìm được những chiều không gian khác, và chúng ta có thể tìm được một trái đất khác ở ngay tại đây. Đó có phải là hướng đi khác, có phải là hướng đi có thể như là rất hay trong thời gian này khi mà chúng ta đang bị kẹt lối.
Okay, so two questions. Okay, the first one is why we need to find out Earth-like planets. We need new energy, or what we need? Okay, new land, new life, new home. Second one is maybe you talking about is string theory. It could be there are many universes, and then we should find out Earth-like planets in other universe. It's not in universe. Two questions. It's okay. So, để cho thầy trả lời nhé.
Yes.
Yeah.
So, to answer the first question, I will a little bit enlarge the question. Okay. For many thousand years, people are looking at the sky and questioning where we are, what are the stars, what are the systems, what is the formation of stars, the galaxies, and so on. And this is the search for life, or planet with the possibility of life development, is only part of the same development and question. People are dreaming from 1,000 years of do we have other places in the universe with living species. And we are absolutely not looking for new energy, new land, new possibilities. It's only fundamental question. And I believe, can you imagine yourself to live here and having no knowledge at all? What are these small dots in the sky every night? Why you have some dots moving and so on, and do not have any idea why you are living. And in the past, people having been, because it only achieved this level of understanding, was always afraid of the relation with the sky, because sometimes you have comets, and they were afraid by this comet, strange object, and so on. So the curiosity of man to try to study this thing, but it's absolutely not based on the expectation of new land, of new technology, or new possibility of to go, travel, and so on. You can try, because you have a lot of story or bad story on this. For example, people say, oh, if, let's imagine we find a planet with life at 50 light years from here, extremely close to the scale of the galaxy. So let's imagine this could happen in a few years from now. You have this kind of ozone signatures in life. Do we have a chance to go and visit these people? Absolutely not. Because you say, if you are, I can repeat, that man have visited only the moon, and it's 1 second of life. And now we are discussing of 50 years of light travel. It's about 1 billion times larger. So I don't remember how long was the Apollo mission. It was maybe 3 days to go to the moon. So if you multiply by 1 billion, it's a lot of years. So you are very optimistic. So you say, okay, we can accelerate this rocket and go faster and faster. But physics law say that you have to pay the price. Because it's not a problem to double the velocity. If you diminish to 1 billion to 500 million, no gain at all. So if you would like really to go, you need to go very close to the velocity of light. But the cost in terms of energy is terrible. So to accelerate the rocket, you need a quantity of energy equivalent to the global energy spent on the Earth for 1 year. So you see, okay, you can dream, but do not forget physics law. It's not a matter to accelerate, push to accelerate the rocket. You have to keep in mind that you are living in the domain where you have to abide to the law of physics. And in fact, we do not have any possibility to go and visit these people if they exist. Okay, after multi-universe, okay, it's one step further. First, we do not know if there is a universe, and after, as I know, we have no chance to go from one universe to the other one, at least at the velocity of light. So, still worse if you are going with the vehicle. So, our universe is already large enough to do a lot of things.
Tôi xin phép là surprise, tổng hợp lại tức là câu hỏi thứ nhất ấy, thực ra vậy là space là một cái có đất mới rồi nhà mới hay là năng lượng mới, mà chủ yếu là câu hỏi là tò mò. Và thực ra là bên cạnh đó thì phát triển thiên văn thì luôn luôn là phát triển với những cái công nghệ khác, cho nên là qua đó thì qua những cái khoa học cơ bản khác nữa, cho nên đó là thì đó là câu hỏi lớn nhất là chúng ta tìm hành tinh khác là bởi vì trả lời cho những cái câu hỏi lớn nhất của con người là tính tò mò. Còn cái thứ hai là có vũ trụ khác hay không thì chúng ta phải biết, chúng ta mới quan sát, chúng ta mới tìm. Thực ra ngay cả những cái tính Toro hay Kepler thì hoặc là những tính ở La Parana ở Chile thì thực ra mới quan sát những cái hành tinh những cái hành tinh mà quay xung quanh các ngôi sao rất là gần thôi. Còn mà nếu đi ra ngoài ngay cả các hành tinh mà ở các thiên hà khác thì chúng ta vẫn chưa có kỹ thuật để mà quan sát tới, cho nên chúng ta cứ quan sát trong hành tinh của chúng ta, và sau đó nếu mà kỹ thuật phát triển thì chúng ta quan sát hành tinh ở các thiên hà khác, để lúc đấy chúng ta mới nghĩ cái phục vụ khác. Như vậy bây giờ còn hai cái câu hỏi khác, là câu hỏi là tôi xin đọc là nếu như thật sự tìm được một hành tinh có sự sống như trái đất thì việc đến hành tinh đó có phải là một vấn đề? Ra câu hỏi này là giáo sư đã trả lời rồi. No way. No way means không có tiền. Không lấy được.
I will enlarge a little bit the question. You maybe have heard about what is called the sensing experiment. Search for and this is coming from search. It's simply big radio telescope and just to listen and to analyze the signal coming from the universe, to have the expectation to find maybe some unusual signal not produced by normal physics. So this kind of experiment exists from something like 50 years. Nothing was discovered. I have no way to say if it's a reasonable experiment or not. If they win and they receive a signal with really not natural kind of feature or characteristic, it will be an incredibly important fact. This will be the proof not only of the existence of life, but existence of developed life, intelligent life, with a lot of technology development. So maybe some people consider this is maybe excessive to try to search for this extreme development of life. But this is a different approach, but it's no way to go. And also no way to answer. You see, that you have to keep a little bit modest. Most of biologists consider that dolphins have some form of intelligence. They have a complex way to connect them and to discuss between them. But until now, nobody has been able to discuss with dolphins. So if you receive some kind of encoded signal from the universe, do you believe that we will understand what they are saying? So we don't have to naive it.
Câu trả lời là có, và chúng ta thực ra chúng ta chỉ thể quan sát những hành tinh đó thông qua những cái phổ giống như giáo sư có chỉ ra quan sát là kim tinh và hỏa tinh và trái đất, thì chúng ta thấy những tín hiệu chẳng hạn như nước hay là CO2 đâu, chúng ta ở quan sát từ xa, nhưng mà thông qua các tín hiệu hóa học đó, các phổ hóa học đó, thì chúng ta có thể đoán là có sự sống hay không hay đâu. Nếu các bạn có hỏi là nghĩ là cái về quan sát cái câu hỏi được đâu.
Relatively simple questions. A comet is only a relatively small body inside the solar system, which is formed by ice particles and dust, gravitationally connected. So it's a relatively, when I say it's relatively, it could be a ball of ice, dirty ice, of about 100 meters of diameter, maybe a little bit 1 kilometer diameter. Okay, it's not really small, but the size of extrasolar planet is really a small body. And this kind of, we know that in the very far outside part of the solar system, we have a reservoir of maybe 1 billion comets. And time to time, one of these comets enter in the inner part of the solar system and start to evaporate, and this is beautiful phenomena we can observe. But it's extremely small scale. It's absolutely not related to extrasolar planets. I will answer.
Tức là câu hỏi là phân biệt sao chổi và hành tinh khí thế nào, thì thực ra là sao chổi thì nó kích thước nó lớn hơn nhiều so với cái hành tinh, cho nên là cái điều đó thì dễ dàng quan sát được hơn.
I will ask you a question to the public. Sometimes you can see a shooting star. A shooting star. Yes, when you have a shooting star in the sky, what is the size of the majority of the shooting stars you can see in the sky? What is typically the size of the body entering in the atmosphere of the Earth?
Câu hỏi là cái kích cỡ cái kích cỡ của một cái ngôi sao băng là bao nhiêu, thì giáo sư muốn hỏi người nghe có ai trả lời không?
Okay, I will give you the answer.
Yeah.
Size is 1 millimeter. So you see that we are looking at the sky, you see this vast twilight, shooting star. It's a very, very small piece of rock entering at very high velocity, and the friction with the Earth's atmosphere ignites this piece of rock and produces long stream of light. But it's absolutely not the same scale. Okay, comet is large, different story. But just to keep in mind that you always have to consider the size of these different phenomena.
Okay. So thì như vậy giáo sư trả lời là em trả lời là đúng đó ha, tức là cái asteroid ấy, tức là cái thiên thạch này là cái kích cỡ khoảng 1 mm thôi, nhưng mà nó rơi vào kích cỡ thì nó bốc cháy thì chúng ta phải xẻ ngang và như vậy thì nó khác với là số chỗ thì nó kích cỡ nó lớn hơn nhiều.
Evidently, time to time you have larger one. About once a year, you have an asteroid with a size of 1 meter entering the high atmosphere of the Earth and producing a huge blast, and with a typical energy of few kilotons. So it's extremely high energetic event. Will be 1 a year. And once every 100 years, you have some dramatic event with maybe with the size of 10 kilometers entering shocking the Earth. It's a completely different story. This happened 16.5 million years ago in Mexico, in Yucatan. Maybe 70-75% of the living species was dead, disappeared. But this is very rare. Don't be afraid.
Okay. Câu hỏi tiếp theo là thưa giáo sư, chúng ta đã có những bằng chứng thiên văn học nào để giải thích về những giả thuyết UFO, là người ngoài hành tinh từng xuất hiện ở trái đất hay chưa? Đó chỉ là sản phẩm của loài người. Thì có câu hỏi khác tương tự của bạn Mai Kim Phi là giáo sư đã từng quan sát được UFO chưa? Giáo sư là có tin UFO có thật hay không? So the question is, did you observe UFO?
What's that?
Yeah, UFO.
UFO?
Yeah, UFO, unidentified objects. And do you believe this is true?
Yes, UFO, it's a very good name because unidentified flying, don't know what it is. So it arrives sometimes, you see some strange effect, but UFO is not equivalent to extrasolar visit of people living here. It's something simply an object where you don't know what it is. And many years ago, at the observatory, we received some telephone calls. I say, oh, we have some very strange light in the sky, and so on. And we took a small telescope, look, and it was simply a high altitude balloon, and with a rising sun, it was sending different kind of light, flash, of big tetrahedra, and with some motion in the wind. So you see that sometimes it's very natural things. UFO is not necessarily something unusual. And as far as I know, 99% of astronomers, astrophysicists do not believe in this kind of system.
Như vậy giáo sư đã trả lời đây thì thực ra cái tên UFO là một tên rất hay, là bởi vì là có thể nó ám chỉ tất cả những cái đó, có những cái bậc nào có thể được bay, chẳng hạn như là máy bay hay là vệ tinh hay là rocket tên lửa hoặc là kính khí cầu thì đều có thể là chuyện đó. Và như vậy thì cái câu trả lời là có tin hay không thì giáo sư cho biết rằng là 99,99% thì các nhà khoa học tin là có người ngoài hành tinh. Và ok, so có một câu hỏi tương tự thì là bằng tiếng Anh, tức là cái ngôn ngữ của chúng ta dùng để mà giao tiếp khác với thế giới là gì? So you can read this one. What language should we use to communicate with the other worlds if we far?
I gave this example of the dolphin. Okay, we have no idea. what could be the communication. You see already between the French people and the Vietnamese, it's not so easy to discuss, but with dolphin or extraterrestrial people, it will be more significant difficulty.
Thì còn câu hỏi khác tương tự như cái câu hỏi mà chúng ta tìm trái đất ở cái kiểu hành tinh như trái đất của chúng ta, thì lúc này trả lời rồi thì tôi sẽ phép là không câu hỏi này nữa. Tiếp theo là tại sao phương pháp radial velocity, tức là phương pháp là vận tốc xuyên tâm đấy, là diễn ra ở người hướng nơi thì chúng ta biết là quay về chúng ta thì chúng ta phải thấy là di chuyển về phía xanh, và nếu mà ra xa chúng ta di chuyển phía đỏ thì chúng ta thấy là từ đỏ về đó được vận tốc xuyên tâm. Thì câu hỏi là tại sao cái phương pháp này, tức là phương pháp vận tốc xuyên tâm là hiệu quả như vậy, vì rất nhiều hành tinh đã được phát hiện ra những phương pháp này. Phương pháp transit thì có vẻ dễ dàng hơn, tại sao lại kém hơn từ phương pháp này? Thực ra cái này thì nhiều sự để diễn được why is radial velocity method is so efficient. The second one is to transit planets but requires as efficient as radial velocity.
For the time being, radial velocity was the first having detected planet. Then after transiting planet was discovered, and eventually mission like NASA mission Kepler succeed to find several thousand candidates. But you have to consider that this object mostly are extremely faint. It's a very narrow beam, and most of them are extremely faint objects and almost impossible to do follow-up studies. So these are only two techniques used to search for planets, but we already have several others. I have not mentioned this technique. We have what is called microlensing, gravitational microlensing. Discovery maybe 10 planets or 20 have been discovered by this technique. Is the fact that you have bending of light due to the mass, and this you can see sometimes one distant star with some amplification to the bending of the light right due to a planet. A few objects have been discovered like this, but once again it's very difficult. You cannot do any follow-up because this was a single event and then after it disappear. In the future we will have astrometry, so if you look at the sky you will see some small movement of the position of the velocity, but position of stars on the sky, that is dramatically difficult, because the amplitude of these phenomena are very small, and so on. So you have different other techniques, but for the time being, I believe the only, no, it's not the only, you have also the problem of timing. Also sometimes you have a periodic signal, and the object move, so for variable stars, things like this, you can have some small, the detection via the shift of the signal, time shift of the signal. But it's true that mostly all what we learned was due to radial velocity and transit.
Thì thực ra là cái như vậy thì cái phương pháp là đo vận tốc xuyên tâm bằng hiệu ứng Doppler thì thực ra là bắt đầu từ khởi điểm của nhật xương. Thì sau đấy người ta thấy hiệu quả, và cho nên là người ta về sau đấy mới phóng cái vệ tinh Kepler và Kourou lên. Thì như vậy thì vệ tinh Kepler và Kourou thì dựa trên cái phương pháp là bắn ngang qua, thì như vậy cái ngôi sao như thế này thì bắn ngang qua thì mình thấy nó bị mờ đi. Như vậy mình thấy cái độ trứng của nó là bị giảm. Thì thực ra là tại vì là lúc đầu khi là quan sát ở dưới thì sau đó những cái năm sau này thì người ta muốn tìm kiếm một cách hệ thống hơn, thì là Kepler bắt đầu được phóng lên và Kourou được phóng lên. Thì thực ra là Kepler và Kourou được phóng lên hiệu quả hơn, là bởi vì nó có thể xử lý là bằng vệ tinh và có thể là phát hiện rất nhiều hành tinh trong một vài năm. Còn quan sát bằng phương pháp đo Doppler thì mình phải đo nên đo cái một nó chậm hơn so với cái vệ tinh. Thì thực ra là cái sau đó là hiệu quả hơn, và thực ra là có những phương pháp khác, cái hai những phương pháp gọi là microlensing, tức là giống như là dựa trên cái gọi là hiệu ứng thuộc tính hấp dẫn này. Thì là theo lý thuyết Einstein như vậy, ánh sáng nó đi gần một cái hành tinh thì nó bị bẻ cong, thì cái đó thì người ta cũng phát hiện ra khoảng 10 cái hành tinh, nhưng mà thực ra là nếu mà để tiếp tục mà quan sát những cái hiện tượng như vậy thì nó rất khó, là bởi vì là nó xảy ra là không phải theo chu kỳ hỏi là như vậy. Có một câu hỏi tiếp theo là tức là chúng ta đã có phóng lên vũ trụ những và gửi theo những dấu hiệu để người hành tinh có thể thấy, họ sẽ liên lạc với chúng ta. Giáo sư cho biết cụ thể dấu hiệu đó là gì?
The problem of communication will dramatically different because if it's a very close star at let's say 50 parsec or 50 light years or something like this, the call will spend several tens of years to go to you, and you try to translate, and then after to give an answer, and they will receive the answer only 1 century after. So, oh, what they will say, oh, I'm not discussing with you. No, okay. We can have some fantasy around this kind of things, but you have to realize that. Imagine you call somebody, some friends, and he will answer only 1 century later. And maybe discussing with different language.
Tôi sẽ có hỏi là thực ra là những cái ngôi sao mà các chúng ta khoảng 15 parsec, thì nhân lên với 3,2 mấy năm ánh sáng thì thực ra là có communicate. Vấn đề thực ra cái câu hỏi communicate với người ngoài hành tinh thì những khác thì luôn luôn vấn đề đau đầu. So you this guys one is signal sent to the space.
Oh. You are okay. The SETI experiment has one is to listen simply, and to see if you have some kind of white noise or different kind of noise produced by the normal physical process, and maybe you can dream sometimes you see something different. And okay, I have discussed many times with some colleagues working in this. They are not crazy people. They are really doing very good technology development and so on, with multi-analyzer on 1 million channel with different frequency and so on. And when they start to do this kind of experiment, suddenly they receive a signal with logical structure not produced by physical process. And what was the reason of this object was the US satellite for military purpose, so not announced with the orbits not known in advance. But this was acting as a proof that the experiment was working well. I don't know if it was an intelligent signal, but at least it was not a physical signal. So it works. In principle, the different kind of noise we can have in physics have some kind of characteristic not the same as we have in communication.
Thì như vậy là tín hiệu thì đôi lúc tức là có một cái viên nó tìm kiếm cái ngoài tên là gọi là SETI, là tìm kiếm có thể là lắng nghe nhận những cái tín hiệu từ vũ trụ, thì thực ra là họ cũng có nhận được những tín hiệu đặc biệt từ không gian. Nhưng thực ra là quả ra cuối cùng thì tìm ra đó là những cái vệ tinh mà của nước Mỹ, thì họ có những cái tín hiệu như vậy, nhưng mà họ cũng có thông báo, cho nên là mình cái đi thu thì mình cứ tưởng là người ngoài hành tinh, thì thực ra là không phải. Thì thực ra những người mà làm ở viện SETI đó thì giả sử họ cũng phải là bị điên đâu, là họ vẫn dùng những cái kỹ thuật rất tân tiến để tìm kiếm. Okay, so hỏi như vậy thì có rất nhiều câu hỏi, nhưng mà tôi bởi vì là chỉ còn 50 phút, thì như vậy tôi chỉ chọn một số câu hỏi tiêu biểu thôi. Những câu hỏi trùng rồi thì mình xin phép là không chuyển đến giáo sư nữa. So, what do you think about Step 922? Tức là câu hỏi là nghĩ gì về cái hành tinh có tên là Kepler 2b.
On Kepler 20, one of the several thousand of planets detected by Kepler, but with one characteristic, that with a mass of something like, I don't remember exactly, but something like 11 times the mass or 12 times the mass of the Earth. So the announcement was already claiming we have discovered a new planet in the habitable zone. I believe it's not realistic, because 11 times the mass of the Earth, the mass of the core, the mass of the atmosphere do not correspond to what is called our possible place for living development or life development. So it's an interesting object. Right now we have at least 10 objects similar to this kind of object, but this one is probably a little bit too massive to expect. You know, the question is not so evident, because if you have a too thick atmosphere, you have no chance to have also life development. And if you have also, if you're too massive, you have a dramatic change in the plate tectonic, in the internal structure. So if you change the plate tectonic, you are playing with the carbon dioxide ejection in the atmosphere. So it's not simple to increase the parameter space by a factor of 10. I believe it's much more complicated problem.
Có một câu hỏi về hạt Higgs thì thực ra thì chúng tôi có dự định sẽ chuyển mời giáo sư và khám phá hạt Higgs cùng với giáo sư, tức là ông François có thể là đến Việt Nam vào hè năm nay, cho nên là câu hỏi này chắc là để dành cho giáo sư trả lời. Giáo sư François. Câu hỏi tức là về câu hỏi tức là có nhiều cái satellite, cái moon ấy, thì là có thể là sống đó có thể là tồn tại đến cả hành tinh. Như vậy cả bạn chị có thể thấy là giáo sư đã trình bày những cái rocky planet, tức là hành tinh đất đá, ví dụ là như là hỏa tinh hay là trái đất của chúng ta, hoặc là kim tinh hoặc mộc tinh, thì đó là những cái hành tinh đất đá. Và những cái thiên vương tinh, diêm vương tinh, hải vương tinh là hành tinh khí. Như vậy thì có sự sống là tồn tại trên cả hành tinh đất đá, nhưng mà có thể là cái câu hỏi này tức là cái tác giả của câu hỏi này tôi nghĩ là không phải là cứ là phải có những cái như vậy thì sẽ có sự sống.
Yes, question 2 is, according to many scientists, life can exist on a rocky planet. And that planet has to have water, oxygen, and so on. But this is not necessary, because everything can happen. Why don't scientists find another life, a natural satellite, and so on? This is a very important point. I put some weight here on the habitable zone, the zone where you have water, liquid water on the surface. But it's true that we have in the solar system at least 2 or maybe 3 places where maybe we will have life. For example, you have one satellite, I will show you. One satellite of part of the big Galilean satellite orbiting Jupiter. You have 2 very nice examples. One is Io. Io is there. Here. It's really active, with volcanoes still very active. And it's a relatively small satellite, it's not so much less than the Earth. Or it is possible to maintain so huge activity on this. And it's very nice, because the answer was given by one of my US colleagues about 1 week before they have taken the picture. And he said, if you have several satellites orbiting Jupiter, in fact you have some gravitational interaction between the different satellites. And so the equilibrium shape of the satellite has to change continuously to accommodate the potential. And if you have this change of the structure continuously, in fact you you have an influx of energy inside the satellite. And this input of energy is so huge that you can maintain the melting of the satellite. You see, this is only eating by mechanical friction and not by irradiation of the sun. So, okay, not interesting for life. But look, this one, the same, is Europa. This was taken with some nice picture, was taken by the Voyager satellite 20 years ago, something like this. And what this mission discovered, that you have an ice shield on the surface with broken line inside. Okay, I have better picture, but it will need some time for me to find them here. And so if you have a nice shield, it's not a glacier, you have a nice shield. And in fact, this small shield of ice is above an ocean. So if you have liquid water below this surface, and you are at a distance of 5 times larger than the Earth-Sun distance, so the irradiation is 25 less than on the Earth. Or it is possible to maintain so an ocean below this, and it's also the same phenomena here, but with smaller efficiency. So it's also friction able to maintain the ocean. So you start to dream that if you have liquid water below the ice shield, do we have the possibility to have living species, maybe bacteria that evolve a very complex life, but is it to have living species below in the ocean below the surface of the sun? And at the present time, some people consider the possibility to go maybe in 10, 20 years from now to send some space mission to analyze if you can find some bacteria. Well, the thickness of the is not known, but it's probably relatively deep. It could be 10 kilometers. No chance to dig 10 kilometers of ice to analyze the water inside. What you can do, much easier. In fact, this characteristic is only due to the fact that when you have a break of the ice, that you have some water in the break, and and you have some frozen line on the surface. So if you send a rocket and analyze only the water in this region here, in this kind of characteristic, you have the possibility, maybe, if they exist, to find bacteria. So this is one first possibility. You have another one, Encelade. Encelade is a companion, a satellite of Saturn, and recently it was discovered that Encelade has some geyser, liquid water going very high in the atmosphere or on the top of the surface of Encelade. If you have liquid water, in addition to some temperature, why not? You have some influence. And the third possibility I will mention, you know that all the missions sent to Mars, year after year, always is the same dream to detect signature of life in the past of Mars. And so next you can ask, do we have still possibility of living species on Mars today? In fact, people are no more so sure of the answer, because you know that on the Earth we have discovered living bacteria at 3 kilometers deep in folds of the rocks of the Earth. And we know that Mars has some volcano in the past, so you have a lot of heats, fossil heats in the ground of Mars. And we know that we have some water underground, so we do not have any proof that we still have the possibility of bacteria living deep inside the surface of Mars. Maybe not. Nobody knows. Evidently, no way to find bacteria, living bacteria on the surface. It's evidently not. But deep in the rock of Mars, maybe. So the story of life in the universe is true. It's a complicated story.
Tôi dịch nhanh qua, tức là ở đây là những cái gọi là cái mặt trăng của cái mộc tinh Jupiter. Thì như vậy là chúng ta thấy là trên kia là cái vệ tinh Ai, nhưng mà mặt trăng Io, thì mặt trăng Io thì có rất nhiều cái miền núi lửa nó phun trào trên đó. Nhưng mà cái đó thì nó không quan trọng bằng cái dưới này là cái gọi là về mặt trăng Europa của cái mộc tinh. Thì Europa này thì là nhiệt độ rất lạnh, cho nên là nó đóng băng, mình thấy những cái băng băng thì là băng ở khoảng 10 km. Như vậy là dưới 10 km thì chúng ta có thể là chúng ta là hy vọng là có là đại dương ở gì đó. Thì như vậy vấn đề làm sao mà đi xuống sâu dưới 10 km để lấy cái mẫu nước hay là quan sát mẫu nước đó, thì có thể là chúng ta lại bắn một cái rocket xuống là chúng ta phá vỡ cái băng ra, và như vậy thì nước nó phun trào lên, và nước phun trào lên thì chúng ta có thể là lấy những cái mẫu đó và chúng ta phân tích. Và gần đây thì có một cái phát hiện khác là người ta phát hiện thấy nước là phun trào trên một cái hành tinh Enceladus của cái thổ tinh Saturn. Thì nếu như chúng ta thấy có thổ tinh thì tức là chúng ta thấy nước, thì chúng ta có quyền nghĩ đến là có thể là có những cái sự sống kiểu, có thể là nó không phải là cá hay là gì, nhưng mà chúng ta có thể là có những cái là vi khuẩn, bacteria, thì đó là câu trả lời của tôi.
This is it's a closer look of Europa with this fold of the surface. And you see, if you are zooming on one region, you can see this complex pattern of break of the surface of Europa. You see this strip here, broken here, continuing here, broken here, continuing here. And this is extremely stimulating to see this kind of problem here. At Encelade, this is a satellite of Saturn with huge geyser. Probably this will be visited in one generation from now. And not so close, it's 10 AU, so it's a complex and expensive mission to go. And so I don't have here, they have discovered some geyser here on the limb of this subject. Okay. So I fully agree that not the full story is in the habitable zone, the liquid water. Maybe you have more complex situation, but we have to start with some first step.
So I have one question for you. Maybe it's the last question. Why is the first detection of exoplanet is so important? So you discover planet in 1995. Câu hỏi là tại sao cái sự khám phá hành tinh đầu tiên vào năm 1995 của giáo sư thì quan trọng đến như vậy?
Oh, the fact that during several, not thousands, but at least hundreds of years, people was dreaming to detect planets and to bring the proof of what is called the plurality of worlds in the universe. So you have a lot of philosophical discussion around this topic in the past century. And today we have the technology able, with the sensitivity large enough to detect this object. So this was the reason why. It's because it's for the first time we have the possibility to detect and study. And what is good for me is incredibly exciting, and to see the quantity of things discovered during the last 20 years. Today we have, I don't know, several thousand colleagues working on extrasolar planets. Yes. So it's the reason why it's so fast moving, because it's opened a new window of what we can do.
Thì những cái phát hiện đầu tiên luôn luôn là cực kỳ quan trọng, bởi vì thực ra trong thời trước khi mà tôi cũng bắt đầu làm về sông Đông Đông thì chúng tôi biết là trước đó là khoảng cả chục năm là người ta tìm kiếm, nhưng mà người ta cực kỳ là thất vọng, và lúc đó thì người ta nghĩ là chỉ có là trái đất là duy nhất rồi, và hiện những cái hành tinh trong mặt trời là duy nhất. Thì nhưng mà đến năm 1995 thì đúng ai là phát hiện ra, thì cho nên là tạo ra một cái cho đến từ năm 1995 cho đến bây giờ thì bây giờ là khoảng 7.000 người là nhảy vô để mà săn tìm cái hành tinh này, bao gồm cả phóng những cái vệ tinh lên để tìm kiếm hành tinh ngoài dưới đất. Thank you. Câu hỏi nào khác?
John Willow was burned in Roma in February 1600 because he said that one universe is infinite and with an infinity of worlds. So I believe I'm not living so dangerous. Yeah.
Cuối cùng là cách đây mà của trong năm thì người ta đã dự đoán như vậy. Đến năm 95 thì mới phát hiện ra cái đầu tiên của nhân sự.
Professor Mayor and Professor No. I believe that we still have many questions queuing right now. However, please allow us to end this session at the moment. As mentioned at the beginning of the program, from representative of Consulate General of France in Quy Nhơn City, Mr. Nicholas would like to have this. Would like to give his closing speech. Mr. Warren, please come to the stage.
Permis de mieux comprendre ce sujet qui paraît parfois mystérieux pour certains. Et je remercie également le professeur Van Barnock pour cette intervention. Mes remerciements vont à l'Université des Sciences et à l'Université nationale du Vietnam qui a accueilli cette conférence, et sans son aide, cet événement n'aurait pas pu avoir lieu. La réussite de cette conférence est pour moi et pour l'Institut français l'aboutissement d'une forte coopération entre l'Institut français, le Consulat de France et l'Université nationale du Vietnam. Un grand merci à vous tous, professeurs et étudiants, qui vous êtes déplacés pour assister à cette conférence. J'espère qu'avec l'Institut français, nous aurons l'occasion de réorganiser d'autres événements en collaboration avec l'Université des Sciences et l'Université nationale du Vietnam, événements qui pourront être organisés ici ou bien ailleurs à Ho Chi Minh Ville. Je vous remercie beaucoup. Merci beaucoup.
Thank you so much for the closing speech. And from representative of the University of Science, Professor Wong would like to present a gift and lovely flower to Professor Mayor. Please back to the stage, Professor Wong and Professor Mayor. Very much, Professor Wong and Professor Myers. Wow, the time is flying so fast. We really appreciate for your appearance on of the this gate today and see you in another day. On behalf of the University of Science, I wish you have a good health and happiness. Thank you and goodbye.